Hello everybody, and welcome back to the second to last installment of Chapter 3. In this video, I want to teach you how to derive the derivatives of inverse trigonometric functions, and I will also do a few examples to help you understand the concepts better. So first, we're going to start with derivatives of arcsine, okay? It's everyone's favorite topic from pre-cal. Alright, so we find the derivative of arcsine, right? Y equals arcsine of x as follows. We're going to start by first using inverse function relationships, and we're gonna make sure that sine y equals x. Okay, that's one of the inverse function relationships where you can just move this. You can do sine y equals x, sine y equals arcsine of x. Okay, now we're gonna take the derivative of both sides. Right now we're gonna differentiate. So we have dx of sine y equals dx of x. Alright, so what do we have here? Well, sine of y goes to cosine of y, right? Cosine y, but you have to remember we're differentiating y with respect to x, which means you're going to have to tack on a dy dx at the back, okay? This is implicit. And then here we have dx of x equal 1, alright? So, now you solve for dy dx, and we get 1 over cosine of y. Okay. Now the division in the last step is safe because we all know that cosine y does not equal 0 for the interval negative pi to 2. Okay, so cosine y does not equal 0 for the interval negative pi to 2. Or I should use close brackets right there. Sorry, because it is equal to 0 for pi over 2 and negative pi over 2, right? So those are parentheses right there. In fact, cosine of y is positive for this region right there, right? So we can replace cosine of y with, so cosine of y, right, is also equal to the square root of 1 minus sine y squared. And you're going to know this because you know that sine squared of y plus cosine squared of y equals 1. Okay, so you first move the sine y over to the other side, and then you take the square root, okay? So what we can do right now is we can say that dy dx equals 1 over cosine of y, right? Cosine of y, which is equal to 1 over the square root of 1 minus parentheses sine y squared, right? You should also note that up here we said sine y equals x, right? So we plug the x in for sine y, right? And so the derivative of arcsine is equal to 1 over the square root of 1 minus x squared. Okay, now your textbook actually explicitly lists this rule. It's on, I can't recall which page it's on, but I have it right here. So if you want to look at it, then you just flip to your textbook and it's going to be right there, right? But the only reason why I make you actually derive the rule is that on the AP exam you might not be so lucky and you might freak out because there's two more. You have arctan and you have arcsecant, okay? And you might not remember which ones which function or which derivative applies to which. So if you have to, then derive, okay? And so I would actually recommend deriving this function a few times, just 5 times for practice, okay, minimum. And with that, let's actually go ahead and do an example, okay? And right here, I also forgot to mention that your x, right? Your x right here, the absolute value of your x has to be less than 1, okay? Because if it's 1, then you get 0 on the bottom, and that's not good. So, let's do example number 1 from the book, okay? Now, example number 1 asks us to find the derivative, ddx, of arcsine of x squared, okay? And this is screaming chain rule at you because you have f of g of x, okay? So again, peel the cabbage. If you saw my earlier videos, you know that analogy, okay? So now we do 1 over the square root of 1 minus x squared squared, okay? Don't let that fool you because the u inside is equal to x squared, so 1 minus u squared, okay? Think about it like that. You also have to multiply by the derivative, ddx, of the inside, right? This is what I call your g of x, right? And this, of course, you just find the derivative of your inside, right? And so this would equal So this tiny part right here is 2x, right? So you just move your 2x to the top. So 2x divided by square root of 1 minus x to the 4th. Alright? And that is your derivative of arcsine of x squared. Okay, that's not too hard. Let's move on to deriving arctangent. Now, arctangent is derived pretty much in the exact same way. So, although arcsine has a rather narrow domain, which is from -1 to 1, right, as we mentioned in the absolute value. Okay, so, well, arcsine only has a limit from -1 to 1, right, because it's limited right here. The function y equals arctangent, right, is actually defined for all real numbers, and as such, it is differentiable for all real numbers, right? So let's write arctangent on here. All right, and so we're going to differentiate exactly as with the arcsine function. Okay, so we have y equals arctan of x. Okay, well first you got to move your tangent over, so now you have tangent of y equals x. Okay, that's your inverse function relationship. Again, you're going to derive both sides, right? So now you have derivative of tangent of y equals your derivative of x. Okay, and so now you're going to do implicit differentiation. Now, as I've mentioned in 3.5, I think, in the trigonometric function derivatives, the derivative of tangent of y is equal to secant square of y, right? And you have to write dy dx. Remember, anytime you're not differentiating with the variable at hand, you have to tack on the dy or d anything dx, okay? And of course, the derivative of x is equal to 1, all right? So now, once again, you move your dy dx over, so you get 1 over secant square of y, all right? Now, your trig identity says that secant square of y is equal to 1 plus tangent square of y, okay? So now what you're going to do is you're going to plug this inside here, okay? So now your derivative is equal to 1 over 1 plus tangent squared, right? And as such, since your tangent of y is equal to x up here, right, it's defined, what you're going to do is you're going to set this equal to 1 plus x squared. As such, your derivative for arctangent, right, your derivative dy dx of arctangent is 1 over 1 plus x squared, right? And your x can be any value here because this will never become negative, right? The denominator will never become negative. So, so this is your derivative for arctangent, and now we're going to do an example to help reinforce this derivative. And as always, I would recommend deriving this a few times as well, because you never know when this is going to show up on your next test, okay? Or whether or not it's going to be on the AP exam, okay? So now we're going to do example 2, okay? Now example 2 says, a particle moves along the x-axis so that the position, right, so now we write position function, at any time t greater than or equal to 0 is xt equal to arctan of root t, okay? And the question asks us to find the velocity of the particle, right? So now, velocity at time equals 16. All right, so what are we going to do? We're going to derive first. So I think I've mentioned this earlier before, but velocity is the first derivative of position, right? Because velocity is speed, and that's change of position per unit of time, right? So there's an extra per time right there. So you're going to have to change position to speed, right? And what you're going to do is you're going to derive tangent inverse of root t, okay? Now treat your root t as u. So as mentioned right here, right, you're going to do 1 over 1 plus root t squared, right? Because that's your u, that's your x technically, right? You got to plug that in. And you have to multiply by the derivative of the inside, right? Okay. And what you end up getting is 1 over 1 plus t, right? Because your root and your square cancels out. multiplied by the inside. This is technically t raised to the 1/2 power, right? So now you're going to move this up, so 1/2 t raised to the negative 1/2, right? And this, of course, is equal to 1 over 2 root t. Okay, now you're going to, so now you have your velocity function, right? This is your velocity function. This is also your first derivative, right? So this is also your first derivative. So now you have your velocity. You're just going to simply plug in 16, right? That's your velocity. That's where you're trying to find. So velocity at times 16, right, equals 1 plus 16 times 1 over 2 root 16. And use your calculator, use your brain, use your hand, doesn't matter. In the end, you're going to figure out that when t equals 16, the velocity is 1 over 136.